castle where the digital dreams come alive. CESCG takes place from May 1 to 5, from visualization to the virtual space. Scientific sessions take their place.
My name is Tereza Hlavová. I'm from Czech Technical University in Prague, and I want to present to you our work on a new visualization framework for Simulink 3D animation, which I've worked on as my bachelor's project. So, what is Simulink 3D animation? It's a tool under the MATLAB software, and it's used to visualize simulations in a 3D scene. So, a user can connect scene attributes to signals in a Simulink model, and these get updated. So, as you can see, there's an example. It's an official example of Simulink 3D animation, and on the right you can see how we did actually enhance the visualization of the simulation. So, how does it all work for a user? A user has to have a scene prepared in a VRML or X3D format. In this, I'm going to show the new updated example of Simulink 3D animation I did for this work. There you can see a red ball object, which is described in this part. There, of course, is a description of the geometry. It's a sphere. And then there is a description of the appearance with materials. In similar fashion, the small platform is described. When we have this scene, we can also create a model in Simulink with VR blocks, which are library blocks from Simulink 3D animation. In this example, there is a so-called VR sync block, which has two imports for Simulink model signals. And these signals are connected to scene attributes of the object. There is an object translation, which is influenced by this part of the model. And then there is the object scale, which is influenced by this part of the model. And when you compile the model and run it, you can see a simulation of a bouncing ball object visualized with our new renderer. So, main motivation for this work was that there has been a push in MATLAB toolbox development to transition user interfaces and other graphical elements to not use Java and other third-party technologies, but to transition this to web technologies. And original Simulink 3D animation uses Java and OpenGL for rendering. We wanted to keep most of the original functionality, of course, and we wanted to enhance the rendering capabilities. So we wanted to introduce physically based rendering, image-based lighting, and shadow casting. And also we wanted to do some improvements in simple collision detection. Here you can see an official example of Simulink 3D animation called VR Octavia, and on the bottom you can see how the example can be updated to have its looks enhanced with the new renderer. So about Simulink 3D animation, or SL3D for short, architecture. Originally, when the user presents a scene, it gets parsed into C++ instances of predefined classes into so-called internal scene in C++. But we are working in MATLAB, so we want to communicate with this scene. There are so-called VR functions for it. These directly modify the internal scene in C++. And there is also a so-called VR canvas, which is used to change rendering options. It does not directly save anything into the scene because there can be multiple viewers connected and each one can have different options. For the variant of the software before our work, there was an implementation of the canvas with OpenGL renderer, as you can see here. The frame gets directly rendered from the scene by doing scene traversals in the internal scene in C++. So, when we want to do some animation, user or editor or the Simulink model calls the VR functions to change the scene by adding a node, setting an object's properties, deleting it, or reloading the scene. this gets instantly changed in the internal scene in C++. But when we want to animate something, we usually want to bundle multiple modifications of the scene together into one animation step, so it doesn't get rendered after every modification, but we have a function VRDraw now to call the scene traversal and render the scene with OpenGL and embed it into the canvas so user can see it. With the new Java-based technologies, we made a new implementation of the VR canvas using new JavaScript renderer, which is built inside MATLAB's so-called UI HTML component, which runs a Chromium instance, and that can display HTML content. The problem is that this Chromium instance and MATLAB, they are not synchronized. These are two different processes. So we needed to solve the rendering differently. There couldn't be done a scene traversal. We needed to keep the scene representation at two places at once, in the new renderer and in the internal scene. So what we did was that when there is a modification happening in the scene, it doesn't only get changed in the scene, but it also gets stored in so-called update queues. And on every VRDraw now call, those update queues get flushed inside the JavaScript renderer, and it imports it and shows the modifications on its side. So, when we were choosing the library for the new renderer, we wanted it to be JavaScript 3D rendering library because that was the task from the beginning. And we had three options, Xfreedom, Xsite, and Three.js. We chose the first two to consider because they natively support X3D, which is the format that Simulink 3D animation works with. And then we also added in Three.js because it's a very popular 3D rendering library, so we wanted to test it too. In the end, the Three.js library won. It's very popular, it has frequent updates, it has suitable license, but it doesn't have X3D support. It has a GLTF format loader though. And from our testing that we did, it can also be used with Emo.js for maybe future work of using more of the physical simulations. And it's imperative, which means that we have direct control over scene load, objects in the scene, their modifications, and rendering. So, from the implementation itself, the SL3D originally supported X3D version 3.3, which didn't support physically based rendering. So we needed to implement new nodes in the C++ internal scene, which was mainly a physical material node for physically based rendering, environment light node for image-based lighting, and adding more fields to already existing nodes, like cast shadow to so-called shape node, or, for example, normal mapping. So, because we have the scene at two places at once, we needed to solve scene export and import. Export from the C++ internal scene and import to the JavaScript renderer. Because the UI HTML component that MATLAB provides and that we have our renderer encapsulated in has only one communication channel, which is text-based, available for developers. We chose to export the scene, all the important data for actually rendering, into JSON format using RapidJSON library. And this is done during the scene traversal or when the scene gets modified. And this modified info that is sent in the update queues, it's only partial info, it's not the whole scene, of course. These nodes, this representation in JSON then has to be imported into the JavaScript renderer. There we implemented all the classes that we needed for the supported nodes. And also we implemented a mechanism in which these nodes accept the updates from the internal scene. We had to do a communication protocol because MATLAB instance and the Chromium instance or the JavaScript renderer instance are not synchronized. So we had to do a message confirmation so that all changes done in the renderer or in the internal scene would get synchronized. We also implemented some user interaction like intuitive navigation and click to select in edit mode, as you can see here. One of the most difficult parts of the implementation were so-called sensor nodes. These are special because they have an output data that a user can read from the scene. And so we had to keep this information synchronized from the renderer, where the simulation or the activity of these sensors was actually implemented, and send it back to the internal scene so a user or Simulink model can read this output of these nodes. On the left, you can see an example. It's a VR maglev for magnetic levitation. It's using a sensor called plane sensor, which transforms a device input onto a plane, and user can read those coordinates. And on the right, you can see an official example called VR maze, which has a robot with so-called line pick sensor. It detects collisions with blocks around it or geometry around it that's defined. As you can see, the robot reads the output of this sensor, behaves accordingly, and also changes the color of the sensors when something is hit. So there are some more application examples that we have updated. Like there is the VR Octavia example running. Then we made a testing scene for a load of GLTF models, which was not possible before, but now with Three.js it was. And we also did some more of rendering testing and editing, as you can see on the video down below. So in conclusion, we have implemented a new part renderer for Simulink 3D animation. It supports most of the original features, but also adds some rendering enhancements, so physically based rendering, image-based lighting, and shadow casting. And it also supports and improves simple collision detection. Thank you for your attention. You can actually try out these features in MATLAB Online or as an experimental branch of the Simulink 3D animation in MATLAB 2024a. With this command, you can set it to the experimental mode and see this version instead of the old Java version. Thank you. Any questions?
Yes. Any questions from the audience? This doesn't seem to be the case, so I will ask a question. So you showed that the visualization is way more impressive. Generally, did you notice that with this Chromium and this message passing, was there some kind of lag introduced compared to the previous implementation?
Yes, there is a bottleneck actually in the speed up. We did some testing on the performance, and it turned out it runs at about 44 frames per second, which the old variant usually does too, but there are some models which are simpler where it can run much faster, and there is a bottleneck in the communication probably, which means that even when the rendering itself is fast, the communication isn't, so it gets stuck on those numbers.
Okay, thank you. Maybe now a question from the audience. Okay, I think then we can go to the next presenter.
Listen to the beat where the pixels play, from rendering to VR. It's a pixel away.